All right, this video is going to be on the second fundamental theorem of calculus. Now, earlier you saw that the definite integral of f on the interval from a to b was defined using the constant b as the upper limit of integration, and x is going to be the variable of integration. However, a slightly different situation may arise in which the variable x is actually used in the upper limit of integration. Now, to avoid confusion of using x in two different ways, most of the time t is temporarily used as the variable of integration. All right, t, temporary, okay? Now remember that the definite integral is not a function of its variable of integration, right? It's a function of whatever is, normally you get an answer because you're using constants. But if you've got a variable in your integration, then that tells you that your answer is going to be a function of whatever that variable is, not the function of whatever your integration variable is, okay? Because the whole point of integrating is to get rid of that variable and get just an answer out. When we're talking about definite integration anyway. So, here we have the definite integral as a number, all right? Here we're evaluating from a to b. These are both constants. F is a function of x, but when I plug in values, I just get a number out. Now, when we look at the definite integral as a function of x, so our answer is no longer going to be just a number. We've got x in our upper limit. We've got a function that's it's t, but it's going to wind up plugging x into it, right? So that means that our answer will be a function of x. So let's take a look at this. We've got f of x equals the integral of cosine t dt. And we want to evaluate this at x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2. Now, the long way would be to just go ahead and say, okay, from 0 to 0, cosine t dt, from 0 to pi over 6, cosine t dt, and just do this for each one of them. That's the long way. The easier way is to integrate it just like it is. So I know that the integral of cosine is sine x, so t in this case, and we're going to evaluate it from 0 to x. So this just gives us sine x minus sine of 0. But what's sine of 0? Sine of 0 is just 0, so we just get sine of x. So when x equals 0, we get sine 0 equals 0. At pi over 6, we get sine pi over 6 equals what? 1/2. Sine pi over 4, we get square root of 2 over 2. Sine of pi over 3, we get root 3 over 2. And then sine of pi over 2, we get 1. So notice we were able to integrate one time and then plug these in because we turned our answer, our capital F, into a function of x, okay? Now you can think of that function f of x as accumulating the area under the curve ft equals cosine t from time t equals 0 to time t equals x, right? So for x equals 0, the area is 0. F of 0 equals 0, okay? But for x equals pi over 2, that means we're looking for f of pi over 2, which was 1. And that was the accumulated area under the cosine curve on that entire interval. So this interpretation of an integral as an accumulation function is often used in applications of integration. Now, in example 3, note that the derivative capital F is the original integrand with only the variable changed, right? So, if we talk about f of x, if we talk about the derivative of capital F of x, we're talking about the derivative of sine. The derivative of sine is cosine, right? So if you take the derivative of a function, but notice that this is of x, but this is of t. As long as we're talking about evaluated from some value to x, then all we've got to do is just change that x, not to the dt, but to here, and we've got our answer. And that's what the second fundamental theorem of calculus really says is if you take the derivative of a function of a different variable, as long as your limit of integration is the variable that you're taking the derivative with respect to, then all you're going to do is just change that variable to that one. An example, the derivative of square root of t squared plus 1 dt from 0 to x. Since this and this are the same, I can just change this x squared plus 1. That's all you're doing. It's a really cool process, and mathematically it's kind of beautiful, but it's really easy to do even if you don't understand what's going on behind the surface. So if you have any questions about that, please shoot me a reminder or ask questions in class.